Question 1 then is a fairly sort of typical titration question. It asks first of all what a standard solution was. Really it's just a solution of accurately known concentration, but if they ask you, it's a good idea to say a little bit more than that and say yes, a solution of accurately known concentration made up by dissolving an accurately measured mass in an accurately measured volume. That's how you would actually do it, and that's then what part B is about. So B asks you how you would actually make 250 cm cubed of this standard sodium carbonate solution. So the first thing is you have to calculate the amount of sodium carbonate that you'd need, and the nasty little twist here is that what you were given was hydrated sodium carbonate. Actually, that's a very common thing for a lot of chemicals. They normally occur as the hydrated form, and so this isn't just a sort of peculiarly perverse question. It's a real common situation, and so it does come up in exams. And the thing to realise is that if you take this stuff and dissolve it, that water of crystallization will just become a small part of the water in the solution. So it isn't a problem. You don't have to get rid of it because you're then adding water back anyway. So all you do is to say, right, I'm going to work out how many moles of sodium carbonate I need, and each mole of this hydrated compound contains a mole of sodium carbonate, so the moles of the whole thing that we need will be the same, and there will then be some water in there as well, but that's fine because that just becomes part of the solution. So do the calculation first. So we get that the moles of sodium carbonate needed is concentration times volume in dm cubed. It's a normal thing with solutions, and it wants 0.05 mole per dm cubed is the concentration. 250 cm cubed is 0.25 dm cubed, so that's 0.0125 moles. Okay, be very careful with your zeros. Okay, there were lots of mistakes in these tests with people getting the wrong numbers of zeros in front of things, so be very careful copying numbers and entering numbers into your calculator and so on. So that's the starting point. And then, as I say, the moles of Na2CO3 is the same as the moles of Na2CO3 10H2O, because each mole of that compound contains a mole of that as well as 10 moles of water. So what that means is that we can just work out the MR of this whole thing, including the waters, and therefore work out what mass we need. Okay, so mass is equal to moles times MR, which is 0.0125, we've just worked out, times the MR of the whole of that, including the 10 waters, is 286. Okay, lots of people just kind of ignored the waters and just put in 106 there. But of course that's not right, because if you weighed out the amount based on 106, a large proportion of that mass is actually water that you're weighing out. It's not sodium carbonate, so you'd get the wrong amount. So this relationship is really important, and then you just think, right, that means that I've got to work out the MR of the whole thing, including the waters. Which is that, and that works out as 3.575 grams. So then you need a bit of practical detail as to how you would take this mass of sodium carbonate hydrated and turn it into your 250 cm cubed of standard solution. So the trick, remember, is that you first of all dissolve it in a smaller volume of water than 250, because if you add 250 cm cubed of water, the final volume you end up with is likely to be bigger than 250, and then you're not going to have an accurate solution. So the first step is to dissolve your 3.575 grams of sodium carbonate in, and then just think of a number that's less than 250. They're not going to, pick you up and anything. So it's just something like 100 cm cubed is sensible. In 100 cm cubed, and you should specify distilled water rather than just water. because so you're going for something very pure here, so you need to use high quality stuff, 100 cm cubed of distilled water. And I think you should probably say what sort of container you would do it in. So in a beaker, and a sensible size of beaker. Whenever you're talking about equipment like this with a particular volume, you should try and specify what the volume would be. So something like a 250 cm cubed beaker would be fine. Obviously not a 100 cm cubed one, because then it's going to be full and you can't stir it round properly. So that would be the thing. So then you transfer the solution to a 250 cm cubed volumetric flask. So again, it's important to specify the size. 250 cm cubed volumetric flask. So a volumetric flask, remember, is something that looks like this. Okay, so it's this shape of flask and it has a graduation line on there, and the idea is that when you fill it up so that the meniscus of the water is just sitting on that line like that, then you have exactly 250 cm cubed in there. So that's what you use for making up these solutions. So transfer to a 250 cm cubed volumetric flask, and then you're going to add more distilled water up to the 250 cm cubed line. And then the final thing is that it's not going to be mixed properly, because obviously you're going to have added your solution at the bottom and then you've added water onto the top, and it's not going to be completely mixed. So you invert repeatedly, which just means you put the stopper in the top, turn it upside down and back again. So invert repeatedly to mix. Okay, so it's just these little bits of practical detail that they put into the exam sometimes, basically to say, have you done some practicals? Do you know how to actually do these experiments rather than just write the equations to describe what's going on? So it is a significant, not a huge chunk of the exam, but it is a significant chunk of the exam, because they don't give you a practical exam and this is what they do instead. Part C gives us some titration data and asks us to find a suitable mean from those data. So there are a couple of things you need to know about how they expect you to do this. The first is that if you do a rough titration or trial titration, it might be described as, you don't ever use that number in calculating your mean. Okay, because the whole point about it is it's rough, it's not super accurate, and so you don't include it. From the remaining ones, what you have to look for are the ones that are most closely clustered, and you have to be careful because quite a lot of people, for example, spotted that those two were close together and they said, oh yeah, those two are close together, so we'll just take the average of those two, and they left the other two out. But actually, if you look, you can see that that one, 27.20, is 0.05 away from that one, and that one in turn is 0.05 away from this one. So those three are equally spread, equally spaced. The only one that's not so closely clustered is this one, because you can see the one that this is closest to is that one, but it's 0.1 away, it's got a bigger gap. So that one you treat as an outlier and leave it out. Okay, and you might question whether you would do that in real life, but in exams it's just a very simple rule. So it makes your life easier because it means you don't have to make a judgment call. You just stick to the rules, which is that you only take the ones which are most closely clustered, but you have to look at all of the data and spot that there were three equally spread ones here. So that means that the mean is just going to be the mean of those three numbers, which is 27.20 plus 27.30 plus 27.25 over 3, which obviously is just 27.25 cm cubed. Part D then wants the equation for the titration reaction, and it gave you a bit of help because we haven't done that much on carboxylic acids, so it told you what the formula of the salt was that you were going to form. So if you remember, the general recipe is that you have acid plus carbonate gives you salt plus carbon dioxide plus water. You have to remember these general patterns of reactions of acids with various things, because you're always going to be expected to make up equations like this really without any clues. They just gave you the formula of the salt this time to make your life easier, because as I say, we haven't really done much on carboxylic acids, but in general you need to be confident that you can put equations like that together without any prompting. So our acid, it tells us, is RCOOH, and we've got sodium carbonate, and it tells us that the salt is RCOONA. Okay, so H plus has been released from the acid and replaced by Na plus to form the salt, in effect, and carbon dioxide and water. And obviously that needs a bit of balancing. Don't ever leave an equation and just hope it balances, because most equations are easy to balance if you just take a minute or two to check them out. And you can see straight away this doesn't, because you've got 2 sodiums there, so you're going to have 2 sodiums on this side, which means that has to have a 2. And so you need 2 RCOO bits, which means you need 2 of those as well. And then if you check out the H2O and CO2, you find they balance straight away. So that's your equation. Now the next thing in part E is, if you like, the heart of the question. This is the titration calculation thing. And this is what you've got to be really confident that you can do, because you are absolutely bound to get a titration calculation when you come to your exam at the end of this course, maybe even more than one. And you need to practice these until you're pleased when you see those, because you think, yeah, I can do those, I know what the steps are. And the only thing that makes it difficult, or it's not difficult, but that you have to watch out for, is that there are an awful lot of numbers in the question, and you've just got to make sure you get the right numbers in the right place. So if you find that you tend to mess these questions up because you put the wrong numbers in, then it's worth almost drawing a picture like this. So obviously this isn't a requirement in the question, but you might just find it helpful just to draw a very quick sketch. It doesn't have to be a beautiful diagram, just a very quick sketch, so that you can picture what's happening in the titration, what substance is where, what volume is actually being delivered in the titration. So it tells you in the question that you take a 25.0 cm³ sample of the sodium carbonate solution you've made up. It doesn't matter that you made up 250, that's not relevant now, because you're talking about in each individual titration. That's what your calculation is based on. So what matters is that using that standard solution that you've made up, you have 25 cm³ of that. So that means that that's what goes into the flask. If it tells you you've got a 25 cm³ sample, that was what you measured with a pipette and put into the flask. And we know its concentration, because you made up the standard solution, so that's an accurately known concentration. So that's what's in the flask, and we're adding the carboxylic acid, RCOOH, and the volume of that that's added, the mean volume, is what we've just worked out in the previous part, is 27.25 cm³. So that's the volume of the carboxylic acid. So the advantage of having a little summary picture like this is that it means you're much less likely to get the numbers mixed up. So let's see where to start. Well, the first thing is that because we know what the concentration of the sodium carbonate is, and we know what the volume is, because we know those 2 things for the sodium carbonate, that's where we're going to start, because if we know both of those we can get the moles, and as always moles is the key. So we start with moles of Na2CO3 is concentration times volume in dm³, which is 0.05 times 0.0250. Okay, 25.0 cm³ is 0.025 dm³, and that comes to 1.25 times 10 to the minus 3 moles. Okay, 0.00125 moles. Then you say, right, that's the sodium carbonate, but we're interested in the stuff it's reacting with, which is the RCOOH, and that's why we need an equation, because the equation relates the moles of the two, and in particular that's where this number comes into play, because what the equation is telling you is that twice as many moles of RCOOH react as of Na2CO3. So we next write down from the equation moles of RCOOH in the titration. And I think it's a good idea to use this form of words. First of all, from the equation, because if you keep writing that when you practice these, it'll remind you to use the equation at this point. But also this bit, the moles in the titration, because that will remind you that we've then got to scale that up to say, yeah, but what was the total moles in the amount that we weighed up and used to make our stock of solution? So if you get in the habit of writing in the titration, that'll act as a prompt that makes you think, yeah, okay, we've then got to scale up from the titration to the whole pot full, which we'll do in a minute. So moles of RCOOH in the titration is 2 times the moles of sodium carbonate, and so we just double that number to get 2.50 times 10 to the minus 3 moles. So yeah, then we come to this scaling up, because we know what mass of RCOOH we had, but that was dissolved in 500 cm cubed. So what we've now got to do is to work out how many moles there were in 500 cm cubed. So we've got to scale up from the titration volume, which is that, up to 500 cm cubed. So if it's obvious to you how to do that, then just do it, that's fine. If it's not, then here's a way to think about it. So that what we therefore have is 2.50 times 10 to the minus 3 moles in 27.25 cm cubed. So that means that we have 2.50 times 10 to the minus 3 over 27.25 moles in each cm cubed. Okay, because we've got that many in 27.25 cm cubed, so if we divide that by 27.25, we get how many moles there are in each 1 cm cubed. And that in turn means that we have 2.50 times 10 to the minus 3 times 500 over 27.25 moles in 500 cm cubed. Okay, so that's how the scaling up works, and if it helps you, you can break it down into 2 steps like that. Work out how many moles there are in each 1 cm cubed, and then multiply that by the total number of cm cubed in the big pot, which was the 500 cm cubed pot, so you multiply by 500. And that comes to 0.04587 moles, or you could write 0.0459 rounded to 3 significant figures at that point if you wanted to. Okay, so here's a sort of summary of what we now know about this 500 cm cubed pot of the carboxylic acid that was made up at the beginning. It told us in the question that the 500 cm cubed contained 3.945 grams. That's there in the question. But we've now worked out, by scaling up from the titration, how many moles there were in 500 cm cubed. Okay, so that's the number that came from part E. So what we're going to do now is put those 2 things together, because if we know mass and we know moles, we can get MR, and if we can get MR, we can figure out what R must be. That's the strategy, and that's commonly the strategy in lots and lots of titration questions, that you figure out the MR of a compound, and then that lets you figure out something that you don't know about it. Okay, so that's the starting point, so we can write down our relationship MR is mass over moles, and then we just straightforwardly put those numbers in. That's 3.945 divided by 0.04587, and that works out as 86.0 for RCOOH. So then you say, right, but I can add up what COOH comes to and subtract that away from our 86, and that will then leave you with the MR of the R bit. Okay, so we write down that COOH has an MR which, if you add it up, is 45.0. So that means that R has an MR equal to 86.0 minus 45.0, which is 41.0. And so we then have to work out what R is that will add up to 41. So the thing to do is to think, well, it's just going to be made of carbon and hydrogen. If there was anything else in it, it would tell you. Okay, so for the purposes of these A-level calculations, we assume it's just carbon and hydrogen unless it tells you that there's something else in there as well. So we say, right, well, how many carbons could that be to add up to 41? And you can see 4 carbons would add up to 48. That's too much, so that's not possible. 3 carbons is 36. That's possible, because that would give you 3 carbons, and that would leave you 5 hydrogens. 2 carbons is 24, so you'd have to have 2 carbons and 17 hydrogens. That's far too many. So the only thing that looks reasonable, which would add up to 41, is C3, which adds up to 36, and then we need another 5. COOH is consistent. Okay, so that's the kind of process that you go through, is just to work out what number of carbons is reasonable, and generally you'll find there's only one possibility there. So then in part G we have to suggest a structure. Now C3H5, you can see that's not a formula for a simple alkyl group, because if it was a saturated alkyl group, that would be C3H7. So what that means is that because there are 2 fewer hydrogens, it's either got a ring or it's got a double bond. So if we hadn't had any further information, one possible answer would have been that. Okay, a cyclopropyl group with COOH, but that's saturated because it has no carbon-carbon double bonds. And because the question says it's unsaturated, then it can't be that. It's got to have a carbon-carbon double bond. So then you think, well, there are only 3 carbons in the R group, so there aren't actually that many possibilities. So we've got 3 carbons and then COOH. So if we've got to put a double bond in there, it can't go here because this carbon would then have 5 bonds. So it's either got to go here or it's got to go there. And again, if that were the only information we had, we'd have to consider all those possibilities. But in addition to telling us it's unsaturated, it tells us it's a cis isomer. So remember, cis and trans is the alternative to EZ as a way of describing stereoisomers, and those only arise when you have 2 different groups at each end, in other words on each carbon of the carbon-carbon double bond. And you can see in this case that wouldn't be true because you'd have this, and so although this carbon has 2 different groups, this one doesn't. So if you swap those 2 over, you'd still have the same thing. So it can't be that, because that can't have a cis isomer. So it's got to be based on this one. And so it just comes down to remembering what cis and trans mean. So your 2 possible isomers based on that would be this one or this one. And if you remember, the way cis and trans work is if you have 2 things the same, one attached to this carbon and one attached to this one, cis and trans describe where they are relative to one another. So in this case, if you imagine a line running down through the double bond, you've got a hydrogen there and you've got a hydrogen there, and they're on opposite sides of that line. So your two identical groups are on opposite sides of the line, so that's the trans isomer. Here, there's your line, and you've got hydrogen here and hydrogen there, and so that one is the cis isomer. So that's your correct compound, but it asks you specifically for a skeletal formula, and so we've got to make sure we draw it correctly, and that includes the COOH group. So your skeletal formula will look like that for the alkene group, and then you have that there. Make sure in all these organic formulae that the bonds connect to the correct atoms, so you are likely to get that marked wrong if you write it like that, so that the bond connects to the hydrogen rather than the oxygen, because obviously that's not the way it works. And if you try and leave it vague by sort of writing something like that and make it unclear, then you're still likely to get it marked wrong. It's got to be very obvious that that bond connects to the oxygen, so that it's written like that. So finally, in question 1, part H is just a straightforward bit of revision. Having worked out what the structure of the alkene is, it asks us for 2 repeat units of a polymer. And remember, the polymers are formed by breaking the pi bond in the alkene group and using the electrons to then form linking bonds to more repeat units either side, like that. So what that means is that your repeat unit is basically going to look the same as your monomer, except that you won't have a double bond there. Most of the examples we've done like this, we've done with displayed formulae, so there's no reason you have to. You can work it out with the skeletal formula if you are comfortable doing that, but it may be safer to go back and just redraw this in the displayed formula, because this is the way we represented most of the polymers that we looked at. Because if you draw it out like that, it's very easy to see what the repeat unit will be, because it's just got basically the same architecture except that it doesn't have the double bond in the middle. So you still have the same 4 things attached to these 2 carbons. Notice again how I'm being really careful to make sure the bond connects to the carbon, not to the oxygens or the hydrogens, and the same here. It's really important that you do that when you draw out formulae. And the point is that the double bond is gone, and those 2 electrons are being used to make linker bonds like that, which is going to join onto the next repeat unit on either side. So that's 1 repeat unit, but it asks for 2. So you just draw the same thing again, connected up by the linker bond there, so you get the same thing like that. And you must make sure you've got the linker bonds on the end. If you leave those off, then it doesn't make sense, because the carbons don't each have 4 bonds. So that's your 2 repeat unit structure. You can draw brackets around the individual repeat units if you want to, but there is no need to do that. If you do draw the brackets though, you've got to make sure that the linker bonds extend through them, and that's got to be very clear when you draw them out.